In this section, I'm going to talk about open channel flow. So open channel flow is kind of mainly applied to weirs, and there's two types. There's a broad crested weir, which I'm going to consider on this slide, and a sharp edged weir, which we'll talk about in the next one. So as I say, it's normally used for measuring the volumetric flow rate going over this weir, which is obviously important for water companies and environmentalists and that sort of thing. So I'm not going to derive the volumetric flow rate for these types of weirs because it's a little bit more complex than the Bernoullis that we've been using up to now. But essentially, the volumetric flow rate, as with any of our systems that we've been considering, the volumetric flow rate in has got to be equal to the volumetric flow rate going out. And you can see effectively there's been a reduction in area here from the bottom of the lake or whatever this is to the free surface, and then the height is reduced now, so is from the top of the weir to the free surface of the liquid. So therefore the velocity must have increased going in here for the flow rate to have stayed the same. So this has been derived previously, so here's a function for a broad crested weir, so it's this constant times by b. Now b is the breadth, so looking at this figure, it's coming out of the page, so the breadth of this weir is effectively the width, and so it's this constant times the breadth times the height, which is the height from the top of the weir to the free surface, times by the velocity over 2g, and this is function to the 3 over 2. As I say, I'm not going to derive this, so you can almost just take this at face value. Now, for a sharp crested weir, the flow's slightly different. So unlike the broad crested one, you can see that there is some flow separation. As the water goes over the weir, it doesn't just come straight down the other side. You can see more pours over, and you have this air gap in the middle. And as I say, I'm not going to derive this, but this can be shown for a sharp crested weir that the volumetric flow rate is this function which has discharge coefficient, again the breadth, which remember is the width, or the length of the weir, and also h, the height of the water from the top of the physical weir to the free surface. Now here the discharge coefficient is actually being found to be a function of the geometry of the weir, so the height of the water above the weir to PW, which is the actual height of the weir. So again, you don't need to worry where this came from. This would have been derived empirically. So what that means is that previous researchers have done lots and lots of experiments at different flow rates with different heights and measured the height of the water above it, and found that this is a good fit, that for this type of weir, this correlation gives you the correct discharge coefficient to find the volumetric flow rate. Okay, so that concludes this lecture. Thanks for listening.